Hello everyone, welcome to the next video. This one should be relatively quick because there's not a lot of math. It's all conceptual. So I want to remind everyone, first, best way to practice with these problems is to try them yourself, and then to go through the answers with this video. Anyway, let's get started. A moderate force will break an egg. However, an egg dropped on the road usually breaks, while one dropped on the grass usually doesn't. This is because for the egg dropped on the grass, well, the thing is, basically, if you drop it on the grass, it's going to hit the grass, and then the grass is going to slowly bend and kind of cushion that blow until the egg finally hits the ground. With the road, it's just as soon as the egg is in contact, the egg has to stop. Now, that's a huge change in momentum in a very small period of time, okay? The grass has the advantage because it extends out that time. So even though the momentum change is exactly the same, the experience is less force. You can see this in the impulse equation. J is equal to F times T. So if you have a really big time, in order to have the same sized J, you don't need as big of an F. So your force is smaller in the grass case. For the road, you have a very, very small period of time, which means you have a really big force, which will break your egg. So change in momentum is going to be the same for both of them, so it's not A or B, but the time interval for stopping is greater for the one dropped in the grass. So that's going to be C. Next one, a lump of clay is thrown at a wall. A rubber ball of identical mass is thrown with the same speed toward the same wall. Which statement is true? The clay experiences the greater change of momentum than the ball. Okay. The ball experiences a greater change of momentum than the clay. Okay. And the clay and the ball experience the same change of momentum. It is not possible to know which object has the greater change of momentum. Well, here's the thing. It's a cone of the wall, rubber ball, identical mass thrown at the same wall toward the clay. Well, which statement is true? Well, you have to remember that the rubber ball is going to actually bounce off the wall. Okay? So here's the example. Say it's moving with a speed of 3v toward the wall, and then bounces away with a speed of 2v. Okay, that means that your velocity has changed from positive 3 to negative 2. Okay, so change in momentum is mass times change in v. And so if you have a really big change of velocity going from positive 3 to negative 2, that's a change of 5v. You're going to have a pretty big change of momentum. However, if you throw a clay ball at the wall, it's just going to stick on the wall, or at least fall immediately straight down. And so instead of that being a huge change in velocity, you'll have a velocity of 3v going toward the wall, and then you will have a velocity of 0 at the wall. So your only change in momentum is going to be that 3v that you stop with. So the rubber ball is going to experience the greater change in momentum because it's going to bounce away and therefore have a larger change in velocity. So that's going to be answer B. Two identical 7-kilogram bowling balls rolled toward each other. Okay, one's moving at positive 4 and one's moving at negative 4 meters per second. What is the velocity of each ball after they collide elastically? So elastically means there is no change in the kinetic energy. It's conserved. And in this case, if you have two objects that are elastically colliding and they have the same exact mass, then they bounce off each other and then they continue moving with the velocities they were originally given. This is a special case scenario where this always works out to be true. So the one that was going negative 4 is now going 4, and the one that was going positive 4 is now going negative 4. So the one moving to the left is positive 4. What is the velocity of each ball after the collision? Well, assuming that they stay in the same order, so the one going to the left is positive 4, that one's now negative 4, so the answer is going to be B. Okay. The Earth orbit is closest to the sun in January, so I'll draw the sun, I'll draw the Earth, and that's pretty close, so that's January. And then as it orbits, it's going to end up farther away, and so we'll say this is July. Okay, so close in January, far away in July. When is the Earth moving the fastest in its orbit? Well, that's going to be January. It's going to be January by a lot, because out here, the planet has a lot of potential energy, mg h. Over here, it does not have as much potential energy, but energy is conserved. So that means more of the energy that the Earth has is in kinetic energy when it's closer to the sun, and less of it is in kinetic energy when it's out farther away from the sun. So the answer is January. Lastly, for a point on a spinning disk in uniform circular motion, which of the following is not constant? So this is basically, you can apply it to any object in circular motion, okay? Which one's not constant? Well, is angular speed constant? Well, in uniform circular motion, yes. Both regular speed and angular speed is constant. And they're asking which one's not true, which one's not constant, so I'm going to say that A can't be right. Angular acceleration. Angular acceleration is 0 for something in uniform circular motion, not meters, rads. Okay? Because if it's moving at a constant uniform speed, then it's not going to be accelerating angularly. Centripetal acceleration, that is actually our answer, centripetal acceleration. So when you have something moving in a circle, you've got this force, the centripetal force. It could be tension, it could be gravity, it could be a lot of things. And that's going to accelerate you toward the middle of the circular path. Now, the thing is, the magnitude, the actual strength of that force and the strength of that acceleration will not change. But when you're over here, it'll be pointing this way. When you're over here, the acceleration will be pointing this way. When you're over here, the acceleration will be pointing this way, in the same direction as the force in all cases. So that means that your acceleration is changing, just not strength. It's changing direction. Now, magnitude of its total acceleration, again, that won't change. So if you're talking about magnitude, how strong the acceleration is, that's not changing. It's just the direction. So that's it for this video, guys. I'll see you in the next one.